But he says
the whole pair is missing, but both of them are not missing anything. Okay, the next speaker is Alex. I'll go for Sander, who's also here. And here he is.
Yeah, hi. I was going to put a photo of Sander like Chris did, but the only photo I can find online, he looks like he's about 10. Sort of unrecognizable. So yeah, I'm going to talk about our recent LICS paper, which is titled this, A Categorical Semantics for Causal Structure. The idea is basically to try to capture something about causality and causal structure of processes in the structure of a category, rather than something we sort of talk about on top of that structure. So the context of this work is this, you can call it a definition, but it's more of an idea of process theories. So a process theory is basically a symmetric monoidal category which tells you what your processes are, and then some sort of interpretation for those processes. So an interpretation of the morphisms in that category as some kind of physical processes, or computational processes, or something. Right, so I'm going to use this graphical notation, which I think everyone here is fairly familiar with. Just to orient everyone, I'm going to write my diagrams from bottom to top. Yeah, everyone's seen this before. Yeah, so with process theories, really the only difference in a process theory and a monoidal category is what we call stuff. So we call morphisms processes, and certain morphisms have special names. So a morphism coming from the tensor unit into some other object is called a state. So we think of that as a preparation process. Something coming into the tensor unit from something else is called an effect. So you can think of this as like a measurement outcome. And something from the tensor unit to itself is called a scalar or a number. These things just sort of float around freely, and a lot of times we don't pay much attention to them. Right, so I draw them like this. Right, so that's basically all the category theory part of a process theory. So what's the interpretation part? Pretty much all the process theories that we talk about come with a special kind of effect, which is called discarding. And we think of this as the process which takes the state of the system and throws it away. So now we have no state on no system. So this seems like a perfectly reasonable thing to do, right? And we draw it as a little bronze symbol. So the utility of having a discarding process is you can say when something is causal, which is just this equation. It just says if I discard the output, that's the same as discarding the input. And then this has an interpretation, which is to say if we ignore the output of a process, so if we discard it, then it doesn't matter what process happened. So you could think if some processes are happening later, I don't have access to their outputs, so it doesn't matter what those processes are or what they're going to be. And that's why we call it causality, because it kind of fixes an arrow of time. So the two main examples I'll talk about are a classical example and a quantum example. For the classical case, I'll take matrices of positive numbers. Those objects are natural numbers, just giving the dimension, and morphisms are matrices of positive numbers. Then discarding is just this particular row vector, which sends a vector to the sum of all of its entries. And then saying that a state is causal means that this diagram equals 1, which is just saying that the elements of that vector add up to 1.
Sorry, positive numbers you mean positive reals?
Yeah, positive real numbers. So including 0, so not strictly positive. So causal states here are probability distributions, and causal processes are matrices where each of the columns sum up to 1. So these are stochastic maps. So this sort of captures classical probability. Yeah.
Would it be fair to say it gives an arrow of time because there's no inverse in this term? Or does the arrow come from somewhere else?
So if I have this causality equation being satisfied, then there's no reason that the transpose or the adjoint or any other way of reversing this thing would also satisfy that. Just like if I take a stochastic map and I transpose it, then in general this thing's not stochastic anymore. If it is, it's doubly stochastic, which sort of is like a stochastic map going both
Time reverse
directions. Yeah, it's a
Essentially,
time reversible
it's time reversible
process.
Yeah.
In substance, even though you can't necessarily undo it.
No, that's, yeah.
There's a sort of smoosh out map, which is not reversible, but it looks the same in both directions. I think that's the technical name for it.
It doesn't even look
Classical smoosh
It doesn't
out-
even look the
smoosh out
same.
map.
It's just, if you turn it around, it looks potentially different, but still fine.
Yeah, so that's the classical case. The quantum case, also very similar in spirit. So I'm just going to call this category CPM. You might know it as CPM of Hilbert, whose objects are Hilbert spaces, finite dimensional Hilbert spaces, and morphisms are completely positive maps. Then discarding is just trace, and then saying that states are causal is just saying that they're trace one. So causal states are density operators, causal processes are trace preserving CP maps or CPs. Right. So if we have a process like this, which has a bunch of inputs and a bunch of outputs, we can ask to what extent these inputs and outputs obey some sort of causal structure. So is there some causal ordering between these things? So what does that mean? Well, we can associate to each input and output pair just a name, which I think of this as like an event, right? So an event A, B, C, D, E. And these events are causally ordered somehow, right? So this says that A happens before B, and C happens before B, and so on. Or A can have a causal influence on B, and so on. And then to respect that causal structure, or to admit that causal structure, means the following. Phi admits a causal structure, which I'll use this kind of validity symbol for. The output of each event only depends on the inputs to itself and its causal ancestors. So if I have a process like this, and I look at some particular event, B, then I can look at what the output of that event is by discarding everything else. So now I'm going to disregard everything but the output of B. And then saying that this output only depends on its causal ancestors says that if I look at these ancestors, then I get a factorization of a process where this output only depends on these three, and then the rest are just being discarded. So respecting this causal structure means for every event, I can sort of focus on it, and it will decompose in such a way. So you can see that the output of that event doesn't depend on anything but its past. Is it clear? I see some slightly puzzled expressions. Anyway.
So, could you give us an example in Petri nets or even structures?
In Petri nets? Probably I can't give you an example on the fly in Petri nets. An example of this, if you consider a process which just has outputs, then this is just a Bayesian network. So this is some big joint probability distribution, and satisfying these causality conditions is just the sort of Bayesian independences. But this allowing inputs and outputs allows you to make sort of quantum generalizations. Right, so here's a very simple example. So I have a process consisting of two events, A and B, with input A and output A prime and input B prime. Now, a one-way signaling process, so this is a process where A could, in principle, influence B, is a process which respects this causal structure. So that means if I discard B, so here I'm focusing on this output A prime, then it only depends on A. So what does this mean? This means that A happened before B. Right? It doesn't, I don't need B's input to know what A prime is.
Just briefly, can you elaborate a little bit more on why you consider pairs of inputs and outputs? Like physically, what does that mean? Because one could think of a process as relating events rather than being on event.
So, I guess the reason I think of input and output pairs is to study things like Bell scenarios, where you think the events are the combination of Alice making a measurement choice and getting an outcome. And you sort of want to look at both of these pairs if you want to study the causal relationships between Alice and Bob. I think there's other ways to do it, but this seems like the most canonical way. You don't really, you're not making any preference over inputs or outputs when you do it this way. So this is a one-way signaling process is something which satisfies this equation. Or if I thought of these things as stochastic maps, you can just see this as this kind of conditional independence. Right? So the marginal over B prime actually only depends on A. And this is the kind of language you're used to reading. So a non-signaling process is a process which respects both of these causal orderings. So this says that this process is consistent with the causal interpretation of A being before B, and also with the interpretation of B being before A. And so in some sense it means that neither one was before the other. Translating this to equations, this is just the usual non-signaling equations, right? Which if I wrote as conditional probability distributions looks like these non-signaling equations.
Dependency graph, was it Poset?
It's a Poset.
Is there any way of combining these two?
Into a single one?
Yeah.
So I could put an A and a B, which depend on a joint C. And in fact, if C is trivial, then the equations that come out are these two. But there's a bit of a subtlety between a process being non-signaling and what's called localizable, which means it's factoring as a joint state followed by sort of two processes.
But you don't want to allow, let's say, Boolean connectives between the event structures.
No, I don't think there's a... In the most general case, you would probably get a set of these things rather than being able to combine them into a single one.
So there are examples of things that are non-signaling in this sense but not localizable.
Yeah. PR boxes, for instance, exist already in classical physics, but they're very much non-local, so they're not localizable. Oh, I just blown your mind.
No, just okay.
So a PR box is just such a black box with classical inputs, classical outputs, right? But it has even super quantum correlation, so there's no way I'm going to be able to realize it as a shared sort of classical correlation. I mean, like
Yes, your global method.
Yep. And then this is also a counterexample for quantum theory, right? Because this doesn't even exist in quantum theory. So if I make an acyclic diagram of processes, it comes with a canonical choice of causal structure. So if I have this kind of directed acyclic diagram, then I can just read off its causal structure. So these processes correspond to these events. And then the significance of this causality postulate, so this discarding the output is discarding the input, aside from its interpretation, I think, is this theorem, which is all acyclic diagrams of processes admit their associated causal structure. So if I look at this, I'm saying it does actually have this causal structure, if and only if all processes are causal. So, and you can check this, it's fairly straightforward. Right, so So we can also, in addition to talking about first order causality, we can think about higher order causal processes. So we can think about some sort of super maps, super processes, which take in boxes and produce other boxes. Right? So this kind of thing is something which takes a pair of boxes and wires them together with this one before that one. Right? It produces a new process. This can introduce definite causal orderings between these things, so it can always put this one before that one. But you can also define these things perfectly consistently in ways that introduce indefinite causal structure. So this is the Pavia switch process, which, depending on a control qubit that you put in, it either causally orders this one before that one, or it causally orders the right one before the left one. So these are the kinds of things we'd like to be able to study. So what we were trying to solve here was basically answering this question: can we find a category whose types express causal structure? So for instance, if I look at something like this, it's really important that I plug a pair of at least non-signaling processes into this thing to get a consistent process out. Because it doesn't really make sense, for instance, to plug a swap in there, because I have somehow I'm creating processes to go back in time. So can I define a category whose types express the causal structure of boxes? And can I define a category whose types express higher order causal processes? And it turns out, actually, in answering this higher order question, you get a nice answer for this first question, at least in some special cases. So an easy way to get higher order processes is to just move to compact closed categories, which I've already kind of done by doing some wire bending acrobatics. So compact closed category, as you know, is a SMC where every object has a dual object and a pair of morphisms. This one I'll call a cup, this one I'll call a cap, satisfying these line yanking rules. So the significance of compact closed categories is they make it very simple to define higher order processes. And the reason that is because in a compact closed category, all processes are states in particular, due to this concept called process state duality. Which means if I have a process which goes from A to B, I use this kind of lollipop notation for process spaces, then that's the same thing as a state in A star B, which you can see just by bending the wire.
Why the lollipop notation? Oh, that's a typing.
Yeah. So here it's not clear why, but at some point some sort of linear logic-y kind of things are coming. But I'll start now. So the point is, every time I have a process, I have a canonical way to get a state, and I have a canonical way to go back. So I can express second order or higher order processes just as first order processes. So they take in this thing, which is a state, and they produce a new state, right? And this W is something which takes something from A to B and gives me something from C to D. And so I can express these things very easily. So to make this a little easier to see what's going on, we make some notation. We treat everything as a state, so everything has an input, the tensor unit. And then we draw states in any shape we like. And so here I've drawn this sort of Pac-Man shaped thing, but really this is just a state W on 4 systems, with the convention that if the wire goes in, then the type is a star, and if the wire goes out, then the type doesn't have a star. And then we plug these things together just by putting caps anytime there's a pair of wires that come together. Right, so it looks like we can now freely work with these higher order processes and make all kinds of nice compositions with them and reason about them. But there's a bit of a problem coming from the fact that we have a compact closed category. And the problem is this, actually an isomorphism on the equation. This isomorphism. So dual distributes over tensor in compact closed categories, which is a nice feature, but has an unfortunate side effect, which is if I have something like this, then I could write it this way, which is something like that. But then because this star distributes over this tensor, the star goes inside, this pair of stars cancel, and actually you see that this thing is just a first order process, which goes from B to A tensor C. So the only thing the types remember is whether something was an input or an output, which you could say it only remembers the kind of whether it was under an even number or an odd number of these sort of lollipops. Right, so everything, all this higher order stuff just collapses to the first order. But unfortunately, this doesn't happen with causality. So being a first order causal process is very much not the same as being a second order causal process. So this W process itself, satisfying causality, is nothing, is almost completely unrelated to the fact that it should preserve other processes being causal. So the types of causal processes are actually richer than compact closed types. In particular, this isomorphism doesn't hold. But then if we drop this iso from the definition of a compact closed category, we get something else, which is called a star autonomous category. So I'll just sum it up here, because I certainly need to refresher on this, having not looked at linear logic for many years. So a star autonomous category is a symmetric monoidal category equipped with a full and faithful functor from C off to C, such that if I let lollipop be defined this way, then there exists a natural isomorphism this way. So it behaves like a closure operation. So that's what a star autonomous category is. It's basically saying that we do have a sensible notion of function space, which we can define in terms of duals. But the duals and the tensor don't distribute over each other. So here's the sort of plan for the rest of the talk. So if I have a pre-causal category, so a category of raw materials, then I can produce a star autonomous category. So a pre-causal category is a compact closed category with some assumptions. I can produce a star autonomous category which captures this logic of causality. So the types really capture the causal structure of these things. I have till 40 past, isn't it?
Officially started 5 minutes late,
So 45.
42.
Yeah, should be fine. Right, so the kind of standard examples of this construction are if I take positive matrices, then I should get something like higher order stochastic maps. If I take CPM, I should get something like higher order quantum channels. Right, so pre-causal categories are categories which give a kind of good raw material category, which means that discarding behaves the way that you would hope it behaves. It's really a collection of axioms that make our theorems true, to be honest. But it's quite nice how much comes out of these axioms. So a pre-causal category is a compact closed category, which has discarding for every system, of course. And for every non-zero system, this number, so this is just the transpose of discarding by cap. This number is an invertible scalar, so this says something like I can renormalize process maps. Yeah?
What's the zero system?
Zero is if you have a zero object.
But
So-
you don't in this case, so
Well,
can't you just say that your zero systems are the ones with dimension zero or no?
well, so you could read this a bit more carefully and say that either D of A, B sub A is invertible, or A is a zero object. So you may or may not have a zero object. In CPM and MAT-R+, you do have zero objects. So, and then sometimes it's handy to have these around. So these were two fairly simple, easily checked things. The other axioms are that C has enough causal states, second order causal processes factorized. So I'll explain what each of these mean. So having enough causal states is really just saying that your causal states, so like your normalized states, are enough to distinguish processes. So if two processes agree on all causal states, then they're the same. So this is like saying if two stochastic maps agree on all probability distributions, then they're the same, which is true in the models that we look at. The more non-trivial one is this fourth axiom, which is second order causal processes factorized. So this says that if for all phi causal, plugging phi into W results in a causal process, then this W was really just a diagram with a hole in it, like this. So there's a causal process here, a causal process here, and all I'm doing when I plug in phi is I'm just plugging it in between these two causal processes. So it's saying that your only second order causal processes are these kinds of diagrams with holes in them.
What is W?
W is the second order causal process.
Yes,
so
but how is that defined? Is it defined in terms of a state, really?
Yeah, so W, using this convention, W is like a state with 4 wires, with 4 systems on it. And then this is contracting this thing, which you could also treat as a state, into it, and getting a causal thing out.
You have examples in which this doesn't have?
What models where this axiom isn't true? Yeah, REL. REL doesn't satisfy this.
Okay.
But and there's a few open ones. So matrices of real numbers, we don't know if it satisfies this, which actually would be quite interesting if it does, because then you can do pseudo-density matrices and sort of funny stuff. Right. So so those are the 4 axioms. From this you can prove some theorems fairly simply. So in a pre-causal category, one-way signaling process is factorized. So this is the one-way signaling condition, and that implies that there's some boxes like that. Well, how do we prove that? We just bend some wires, and we see that one-way signaling processes are really just the same as these second-order causal processes. Applying this axiom that the second-order causal process factorizes gets the factorization of this one-way signaling process. So just some sort of diagrammatic bending of wires. One that I think is more interesting, or at least we gave it a much more fun name, is this no time travel theorem. So this says that no non-trivial system, A, admits time travel. That is, if I have a causal process like this, then connecting this input to an output, if that's causal again for all phi, then A has to be trivial. So how do we show that? Well, I can define a causal process this way for any causal psi, and then if I apply the fact that plugging this thing into this process yields a causal process, then I get this equation here. But then that implies that this thing is second order causal, so it factorizes. Now the only causal effect is discarding, and the only causal state is, well, some causal state like that. So what do we get? We get rho after discard is 1, and this is just causality. Discard after rho is 1. So A is isomorphic. It's I. And so there can be no time travel. Cool. So a process is causal if it preserves the set of all causal states. So you can prove that in the pre-causal category as well. That is, it preserves this set. Right? So we define this construction, this cause C, by equipping each object with a set of causal states, or a generalization of this set of causal states, and then requiring the processes in that category to preserve it. All right, so we want to capture whatever properties of this set make it well-behaved for making a categorical construction. So the first thing you can notice is that if I have any set of states, I can define the dual of that set, which is the set of effects, which is normalized for all those states. So it sends all those states to 1. Right? So that gives me a set of effects. If I dualize again, I get a set of states again. And then if that's equal to the set of states I started with, I call that set closed. Right? So being equal to its double dual, I'm going to call closed. So another property of the set of causal states is that if I renormalize discarding, well, first of all, discarding is in this dual set. And if I renormalize it, I get the maximally mixed state. So I get something that's in that set of states. If I make this a symmetric property, so symmetric between C and its dual, and I say if a set of states is flat, there exist invertible scalars, lambda and mu, such that lambda max mix is in C and mu discard is in C star. So I call that flatness. Now, here's the main definition. For any pre-causal category, the category cause C has as objects pairs, A, and a set of states, which is closed and flat. And then a morphism is just a morphism from my original category, which preserves that set of causal states. So, main definition, here's the main theorem. Cause C is a star autonomous category. So we define the tensor product as we just take all the product states from these two causal sets, which isn't closed, and then you close it by taking the double dual. The tensor unit is just I with 1. 1 is the only causal scalar. And then the dual is you just take the dual and then the dual of that set. And that makes a star autonomous category. Right. So, the nice thing about this is our original 1 connective of tensor become 3 sort of interrelated connectives. You have a tensor, you have a par, which is the De Morgan dual of the tensor. So you can think of that as like and, this is like or, and this one's like implies. So we have 3 different ways to combine systems to make bigger systems. And intuitively, tensor is like the smallest way I can make a joint state space. So it's the smallest closed space, which contains all the product states. Par is the biggest way I can make a joint state space. So this is the biggest set of joint states, which is normalized on all the product effects. So if you know, like GPTs, this is a bit like the minimal and the maximal tensor product. And then Lully, because of this, is the space of all causal state preserving maps. Right, so for first order systems are things of this form. Then if I compute this tensor product, I see that it's the double dual of this thing, but then the dual of all these product states is actually just discard. So this is all causal states. And if I compute the par of this thing, well, here's the definition of the par. Now the only thing in here is discarding, the only thing in here is discarding. So I can simplify like that. It's all causal states. So for first order systems, tensor and par are the same. Which is why you might think, why have I never heard that there's 2 ways to make the joint state space of a quantum system? Because at the first order, they're the same. However, yeah, I wouldn't have wasted your time showing you that definition if that was always the case. If I make the par of 2 of these things, so now this is causal maps from A to A prime, causal maps from B to B prime. Well, I can replace these lollies with pars and stars, do some juggling, and then ultimately I see that if I take the par of these 2 things, I get the space of all causal maps with inputs A and B and outputs A prime and B prime. So that's nice, it looks big. You expect the tensor to be smaller. And it is. So if I take A lolly A prime, tensor B lolly B prime, I get all causal non-signaling processes. And the proof of this is actually consumes a pretty decent chunk of the paper. But the idea is basically that you, rather than looking at this type, you look at its dual, and then you show that that dual is normalized for all non-signaling processes. And this is a totally graphical proof, but you really use all the axioms, quite a chain of lemmas. Right, so you get this kind of refinement of causal structures, where this you have this sort of smaller joint system which embeds in a bigger joint system. And in fact, this embedding actually holds from a kind of standard star autonomous theorem, which is that if I is isomorphic to I star, then tensor always embeds in part. So you could ask if there's other stuff in between, of course, between this sort of little one and this big one. And the answer is yes. So one-way signaling processes are actually processes of this form, where you take your lollies and you sort of nest to the inside. I think I'll skip that. You can also define things like in-party non-signaling processes, just n-fold tensor products of these things. Quantum incomes, so this is like you can use these to represent something like protocols or games, where you sort of got an input and output, and I'm allowed to do something else and then input it back in. You can represent this as just nesting all to the center. You can compose these things, so you can really prove if I take two of these cone things and I put their teeth together, then the thing I get out at the end is just a causal process. You can get indefinite causal structures. So here's a quantum one that you can use to win some causal game, and here's a classical one you can use to win some causal game. And these are all inhabitants of the dual of this non-signaling space. And one of the things that I think is probably the coolest is the internal logic of star autonomous categories is this multiplicative linear logic, which means you can take kind of off-the-shelf theorem provers and actually prove theorems about causality. And if you'll endure me about 5 extra minutes, I can show you how that works. So here's a very old linear logic prover called LL prover. Visible? Yeah. Great. So, for instance, say I want to prove that this one-way signaling thing really does live between non-signaling and arbitrary processes. Well, a one-way signaling thing looks like this. So arrow is lolly, and so on. A arbitrary process is this, plus is par. If we get to prove it, then it gives you a nice proof tree, which can also be made in LaTeX to write your papers for you. Similarly, if I take this thing, which is a non-signaling process, then
What's the star?
star is tensor. Then this non-signaling process implies, which means it embeds in this space of one-way signaling processes. So it says it's a stronger restriction. Yeah, I think that's basically it. lots of stuff with it. Here's the paper. Actually, a lot of this sort of grew out of Paolo sharing this draft with us a while back, where he was doing it specifically for CP maps, using Choi Yamokovsky to encode all this higher order stuff. So really, this is a lot indebted to that one. But yeah, that's what I wanted to say. So.
Going back to your time travel.
Yeah. Should I go back to the slide, or did you just?
So the way you set it up is exactly the way Deutsch was talking about in the original his original scenario. So there he showed that there are solutions to the equations of quantum mechanics that are consistent. He's got the fixed point theorem. But what you've got is something stronger that's ruling out that. So I'm trying to figure out, is there an easy way to see what extra you need to add to quantum mechanics equation 4 to rule out closed time mechanics?
Quantum mechanics in equation. So you could say, instead of taking CP maps, you could take some sort of formal theory of quantum mechanics where everything's just modulo the equations of quantum theory. And then see what extra you need to add. I think it would be something quite a lot like this axiom 4. So this fact that you have no... So saying that your second order process is factorized is really saying I really have no non-trivial higher order processes which are normalized on all channels. So it really says that they are all secretly first order processes. Whereas this time link really is a non-trivial higher order process. It has to be. Otherwise you get this kind of trivialization.
So there is definitely something in, if you apply what you've done to quantum mechanics, there's more structure there than in standard quantum mechanics. So you want to define that.
Yeah, I guess, depending on how you define standard quantum mechanics. So certainly, this structure is already in the category of CP maps, for instance. But you could say that that's already putting much more in than just the kind of basic kind of equational presentation of quantum theory.
Yes, this is essentially multiplicative linear logic. That's a fair comment. It's a model of multiplicative linear logic. Yes.
Yeah.
Now, the usual story in compact closure is that the exponential of linear logic represents classical information. But when you're jumping to the star autonomous setting, you're getting the full multiplicative linear logic, and you have a split between the two exponentials, of course, and why not a linear logic. So, personally, I've never been completely convinced that the exponential corresponds to classical information. So I was wondering if you had any comments about how it would actually split when you move to this higher order setting.
So we thought of, it's not totally obvious how you even want to define exponential.
Yeah.
In this category, so star autonomous doesn't require you to put that in.
Yeah.
But I don't think it's anything like classical information. If anything, it's something like throwing away causality restrictions. So one thing you can do is you can make bang A be the one which declares now everything in A is a normalized state. Which means now it's very easy to make maps into A. Because preserving normalized states is trivial, trivializes. If you take the dual of that, you get why not A. That says that nothing in A is a normalized state. Which means it's very easy to define maps out. Because now you have nothing to preserve. But then, yeah, you need to put some sort of co-monoid structure on it, and yeah, it's unclear exactly what to do there. But they do definitely split. They're very much different constructions.
But why not A have not enough causal states in that sense? Since nothing is causal.
Well, so enough causal states doesn't refer to these sets C. It really refers to the set, the actual full set of causal states. So all
In the
the,
original category.
yeah. So
Oh,
all the
okay.
states which
Okay.
satisfy this causality.
Okay.
So in some sense, that's kind of, that happens before you make the construction, just to kind of get things rolling. Yeah.
I think the restriction to probabilistic systems like Bayesian networks you mentioned at some point, it's probably very interesting in the sense that you can think of a joint distribution to begin with as a sort of prior, and then this causal order tells you the way in which you can factorize it in Bayesian network. This is actually something we are working on. It's very close to this part, so it looks like you're doing some of the quantum generalization of this, but this could be an interesting particular case.
Yeah, I'd really like to understand this classical case better. I've been chatting to Bart some, kind of trying to move these things a little.
I was wondering, you have this validity sign there,
Mm-hmm.
saying like something like it meets a causal structure, causal order, something like that.
Mm-hmm.
But this is not in the paper, is it?
No, the first 8 slides or so, this was actually in another paper that's in the works with Bob Cook and Matty Harden.
Okay, which is not available yet.
No.
Okay.
Still in hiding.
Okay.
But actually, that paper grew out of giving a talk about this stuff and trying to motivate it with this sort of picture using causal graphs and stuff.
Okay.
Final slides, Alex?